everyone. My name is Xiaofan. I'm a PhD student from UC San Diego. Today I'll present our work, Evolve, Enhancing Unsupervised Continual Learning with Multiple Experts. In this work, we focus on the problem of continual learning, which is defined as how to continually learn over time by acquiring new knowledge, as well as consolidating past experiences. The key assumption of continual learning is that the surrounding environment is continuously changing. Some real-world application examples could be the self-driving vehicles and the AR/VR devices. The key challenge of continual learning is catastrophic forgetting, which means we forget the important knowledge that we learned in the past. While great progress has been made in continual learning, there's still a gap between existing continual learning algorithms and real-world deployments. We recognize that this barrier is mainly due to two reasons. The first one is the real-world streaming data is very unpredictable, and secondly, real-world applications is usually lack of supervision or prior knowledge. In this work, we specifically consider the unsupervised continual learning problem. Most existing works in UCL rely on various prior knowledge to produce good results. As we mentioned before, these prior knowledge may not be available in real-world applications. For example, this first line of work, focusing on using variational autoencoder, usually assume multi-pass data. And the second big group of work assume task-based continual learning, so they assume they knew the task labels and also the task shift boundaries. And the third group of works, they assume a few labeled samples from each classes, so they violate the no class label condition. While STEM is the only work that eliminates all of these assumptions, it requires very dataset-specific tuning on the hyperparameters. As pointed out by a recent paper in ECCV22, another separate line of work has shown that using self-supervised learning methods with a replay buffer can alleviate catastrophic forgetting. However, the problem is that it is unclear and uncertain on how to effectively learn new patterns in an unpredictable world using self-supervised learning methods. In this work, in contrast to all of these existing methods, we aim at closing the gap between continual learning algorithms and real-world applications by eliminating prior assumptions. Our contributions is threefold. In the first part, we conduct an empirical study of existing self-supervised learning baselines using a replay buffer. We want to answer the question that whether existing SSL is sufficient for practical applications. We tested it on CFR10 as an image set dataset example and Stream51 as a video dataset example. And we compare against IID data and temporally correlated data streams. For the SSL, we evaluate the commonly used baselines, including SimClear, BYOL, SimSam, Barrel Twins, and VIC-RREC. Here is a snapshot of our empirical study results. The x-axis of these plots shows the training step as we introduce more streaming data, and the y-axis shows the KNN accuracy of the target model. The key takeaway here is that all of these existing SSL baselines, even accompanied with a replay buffer, experience a significant accuracy drop when applied on the video dataset as compared to the image datasets, and especially on the temporally correlated data streams as compared to the IID streams. So the result here supports our insight that existing SSL baselines are not sufficient for real-world scenarios. To address that issue, we propose Evolve, a hybrid unsupervised continual learning framework that doing self-supervised training on the local client and expert-guided training on the cloud. And we only transmit a small set of data and intermediate features between client and cloud to minimize the communication costs. By using this design, Evolve has two key advantages. Firstly, although we did not assume any prior knowledge, by using a very diverse set of pre-trained expert models, we're able to choose the appropriate expert to help to guide the training of the target model when encountering the proper data. And secondly, to address the high computational cost of running these large expert models, we designed this hybrid framework between cloud and client. So we only run the expert models in the cloud, and that will alleviate the computational expense. So one round of learning in evolve happens as follows. First, once we have the streaming data, we'll combine it with the memory buffer to obtain a local data named X. And on the local client, we pass that X through two-way augmentation and use the self-supervised learning loss to train it on this client. Then we transmit a small subset of the local data to the cloud and their corresponding center kernel matrix also to the cloud. Then the transmitted data will be passed through several big pre-trained experts and will compute their corresponding center kernel matrix. And these information are combined with the client's information to compute HSIC score, which is for distilling the knowledge from the expert and apply to the target model we want to train on the client. Additionally, we propose a dynamic weight adjustment procedure to adjust the different importance value. Specifically, Evolve has two key designs, and our key idea is to use this HSIC score to distill the knowledge from the experts to train the local target model, which combining them together. And this is how we define the expert aggregation loss at the cloud. And we add another additional coefficient as expert weights in front of the HSIC score. And the second key design in Evolve is exactly this dynamic weight adjustment based on a confidence matrix that's shown here. But this confidence matrix is inspired from the contrastive predictive coding. And we want to emphasize that here we use a moving average based updates to adjust the weights, which is very important as we show in our results, because it is able to achieve a proper balance between the historical and latest data. In the evaluation setup, we conduct comprehensive evaluation across image datasets of CIFAR10 and TinyImageNet, and video datasets of Core 50 and Stream 51. And we evaluate across 3 different data streams of IID, sequential, and sequential with imbalanced classes, which is referred to, which connects with the temporal-correlated data streams. And we compare against the latest unsupervised continual learning baselines and also the supervised version, and we adapt it to the unsupervised scenario. For the target model, we employ ResNet 18, and for the expert models, we use the pre-trained ResNet 50 and swing transformer that are trained on ImageNet, and they can all be downloaded from Torch Vision. And for the metrics, we use the KNN accuracy and linear evaluation accuracy. Here we show our main accuracy results. For more evaluation results, feel free to check out our paper. But in a nutshell, the key in the main evaluation, we show that using Evolve, we are able to outperform the top unsupervised learning baseline using the same self-supervised learning backbone by up to 20% in KNN accuracy and up to 53.7% in top 1 linear evaluation accuracy across all 3 data streams. In conclusion, in this work, we study the unsupervised learning problem, and our key motivation is that existing unsupervised learning algorithms cannot generalize well to real-world scenarios due to unpredictable streaming input and lack of supervision and prior knowledge. We propose a general expert-guided continual learning framework called Evolve, with local self-supervised learning on the clients and expert-guided learning training on the cloud. It has 2 key designs: the expert aggregation loss at the cloud and the dynamic weight update mechanism. In the results, we show that Evolve outperforms existing UCL baselines on both image and video-based data streams using the same SSL backbone. If you have more questions, feel free to contact us, and feel free to check our code on the GitHub.